Alright, so in this section what we're going to do is take a look at a situation where we start off with an equation that's not quadratic to begin with, but with some tricks and some patterns we can basically change it. So before we start looking at that pattern, let's just recall again what it means to be a quadratic. A quadratic is an equation where our variable, right, is raised to the second power. And basically it's a polynomial, right? We could probably be more specific. It's a trinomial, right, of degree 2. And so what we've seen is we can usually write these as ax squared plus bx plus c equals to some sort of 0. So that's a classic quadratic. So with the trinomial, it's a polynomial, we can see that the variable at its highest is raised to the second power. And so that's what makes a quadratic. And of course we know how to solve that in several different situations. So with that understanding, let's go back down here and take a look at these 6 equations that I have, and you'll realize that none of them are quadratic. This one has a degree 4, which makes it not quadratic. Right? This has a square root, right? And x is to the first power here, which is not quadratic. Here this almost looks like a quadratic until we take a note that the variables are raised to negative power. So this is not quite quadratic as we would see in the traditional sense, where things are raised to the second power. D is kind of like B. Our x is to the first power and they're at square root. And then this is kind of crazy, right? We are raised to the second power, but within that second power we have something raised to a second power. So if we were to expand this out, right, we'd actually get back up to here, which would be x to the 4th. And then this one's really crazy because we are raising our x's to the 1/3 power and the 2/3 power respectively, which again doesn't match what a quadratic's supposed to be when we're raising things to the second power. So initially, when we look at all 6 of these equations, none of them are quadratic, and so we wouldn't think about doing quadratic things with them. We would do other items. Like for here, we've learned we can isolate the square root and then square both sides and get rid of it, etc. So there's other ways we can do these. However, but when we look really closely at these, we can actually see a pattern that's involved that we're going to take advantage of throughout this section. If you take a look at the middle term right here, which is x squared, if I was to square it, right, and using our rules from earlier, right, where we would multiply the exponents together, what you end up with is the variable part at the very beginning. So let's see if that pattern persists. So I'm going to take the variable part here, which is the square root of x, and then if I square it, right, taking the square of a square root undoes it, and we are left with what's sitting out in front there. Same thing here, right? If we were to concentrate on that middle part, x to the -1, and then we square it, right? Again, using the properties of exponents, where we multiply the exponents, we end up with x to the -2, which is the variable part out front there. This one's similar, right? If we concentrate on the middle variable part, which is the square root of x, squaring it, we get x, which is out in front here. This one's a little odd, but if we look at this, treat this whole part as the variable part, when I square it, I obviously end up with what's in front there. And then same thing here, if we concentrate on that middle part, this is x to the 1/3 power, and if I square it, this is, again, we're going to multiply exponents together, and of course to multiply fractions together, it's top to top, bottom to bottom, and we end up, right, with what's up front there, right? And I hope that was on the screen there. Okay, so we can kind of see that all of these have a pattern, that if I take the middle term, right, or excuse me, the variable part of the middle piece, and I square it, what I get is the term out in front. The other pattern you'll see is all of them have 3 terms, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right, 1, 2, 3, and 1, 2, 3. So they all are very, very close to having a trinomial, right, 1, 2, 3 terms, They're all set equal to 0, which is kind of nice. And the variable part in the middle, if we square it, we get the variable part at the beginning. And so what we have here, each one of these is what I playfully call, a hidden quadratic, because they initially are not quadratic, but they all have 3 terms in them. And if I take the variable part in the middle and square it, I end up with the variable part at the beginning. And so that's a hidden quadratic, or what the book calls, I think they call it equations that are reducible in quadratics or quadratic form, or whatever the case might be. And so what you're going to, now that we've recognized that all of these are hidden quadratics, we're going to learn a little bit of a trick where we can convert it to a quadratic, use our quadratic things to solve it, and then convert it back. All right, and so I playfully call it the hidden ball trick. Right, I always have some weird names for stuff, but you can call it the hidden quadratic trick, the hidden ball trick, the substitution trick, but we'll see that coming up. But now that we've established the pattern, right, on to some new videos on exactly how we can solve all these equations using that trick in a video coming soon. See you guys in a moment.